Hello, everyone. Can you hear me? Okay, great. So, without wasting much time, we'll kickstart with our presentation. So, this is Group C, consisting of Mike, James, and Jason, and we'll be presenting on supply chain behavior during disruptions or extreme events such as hurricanes. The next slide. So our outline for today's presentation is we'll kickstart with the problem statement or objective and move to architecture vision, then touch on our business architecture. We'll dive into our information and technology architecture. Then we'll display our results to the team and we'll show our 3-year roadmap of how to execute this digital twin. So with the problem statement and objectives. So the problem we are tackling here is extreme events effects such as hurricane on freight or network routes. So we are looking at how we will be able to help our industry partner to be able to make predictions and understand and have insights of how hurricane or extreme events affect freight network. So currently there's no system that is able to help our industry partner to be able to understand how the extreme weather events such as hurricane will be affecting freight and how it also recovers with time. So our solution is an AI-powered digital twin where we are looking at bringing data from various sources, wind data, meteorological alerts, and also GIS to be able to create a digital twin which will allow our industry partner DOTs and even freight companies to be able to tell how extreme weather events affect the freight network. So our data, we are targeting track rates and traffic where we'll be looking at WIM simulated data, hurricane data, and GIS data. Next slide. So for the objectives of the project, we are looking at building a data-driven digital twin where we look at incorporating freight data, WIM station data to be specific, hurricane data, and also GIS data. And together we'll be able to create a contextual digital twin that is able to inform decisions for our industry partner. It will also be looking at analyzing corridor importance and disruptions, how some critical freight routes are being disrupted during the hurricane process, and also to understand the impact of hurricane on movement. The next thing too will be informing strategic recovery decisions to help DOT freight companies as well to be able to make informed decisions during the event of hurricanes in order to optimize the flow and keep the freight network going. Next slide. So where did we get our data source from? So our data sources are actual real world data where we touched on WIM data, weigh in motion data from the Federal Highway Administration. We also used NOAA data, the National Oceanographical Administration data for the alerts, and also we used WIM simulated data in XM Pro, which was a great platform, and we mimicked the actual WIM data that's being used in real life. Next slide. So I'll move on to Jason for Jason to take over. Thank you.
Thank you, James. I'll take us through our architecture vision. So to start us off with, our industry partner gave us three main focus areas to look at. One was data management, workflow development, and feature enhancement. So starting off with our data management, currently the current status was only historical WIM data was available. You have to rely on third-party telematics, and all the information isn't synced together. And all the data is kind of siloed off into its own thing, so you're not really able to read it together. For workflow development, uh, going into getting that data to not be siloed, to get it all integrated together into one platform. And then for our feature enhancement, like James was saying before, is utilizing AI to essentially give us a dashboard where we can provide a predictive insight, correlating freight data from WIM stations and hurricanes. So going into our request for change, some things we would need, geospatial data integration, real-time data harvesting. So essentially utilizing something like ArcGIS to have that geospatial data and integrate temporal data so that you're able to get predictive insights into natural weather events such as hurricanes, for example, Florida, and road networks for freight. Develop workflow for utilizing post-processing pipelines to build pipelines to essentially be able to display trends of data, and then moving into AI-driven predictive modeling, which would be a future tool to implement to essentially have some kind of tool in our application to provide predictive like insights into what to do in those situations. So in order to kind of evaluate what should be done, we looked into our Digital Twin Consortium capabilities periodic table. We went through it together and we identified essentially what capabilities are needed to create this digital twin for an industry partner. So we identified essentially anything we felt that was needed with an L, and then we did a assessment based on what level we believe it's currently at. And you can see that in the legend on the bottom left, 1, 2, 3, 4 basic up to advanced. And then overall, our architecture vision is essentially taking our data inputs, which would be outlined by our data stream, the trek weight data, hurricane data, and GIS data, incorporating it into a digital twin. And then the last stage would be the AI predictions. So moving down into our business architecture, the main things we hear about in our situation is the link between the carrier going into this is essentially from the Department of Transportation events that happen during a hurricane. So essentially for freight, it's delivery on schedule, yes or no. We look at it as is the disruption because of weather? Yes. And we look at it if it's a hurricane. Then this is from DOT on procedures on what the phases are of a hurricane related to freight. So you have a pre-landfall phase, or that's essentially the preparation, the landfall phase, where freight is impacted, post-landfall, where you slowly get back into nominal operations, and then finally, in the final phase, you get back into not normal operations. So now passing this on to Mike.
Yeah, thank you, Jason. So now we're going to talk about the information architecture, which defines the data that feeds the digital twin. It's a very important part, as you could see in our periodic table, heavy emphasis on data services. So first we did an assessment on the current state. When we talked with the sponsor, these are the current data sources that existed. And as you can see, they were rather siloed. So the first data source, we talked about the weigh in motion data, and then the weather data, and then the geographic data to add context. And you can see the data content within each of those data sources, and then the decision information. And we decided that the decision information that each of these data sources provided was suffice, and we did not need to add any other data sources. But we did need to add data pipelines and do some data wrangling, which you can see in our future state. Next slide, please. So this is the future state that we proposed. And as you can see, it aligns all the data sources within one application, which we use XM Pro Data Stream or Data Designer. And you can see the data pipeline. It joins all the content into one data repository. And then we're able to pull that information into our application and utilize what is needed for the analytics portion of the twin. So that's how we handle the current and future state for our information architecture. Next slide, please. And this is an example of what our current future state architecture looks like. And as you can see, the data on the left-hand side, that's our WIM and weather station data. And we joined it. We did some contextualization. We walked through, had to add some attribution so it can be read in the application designer. and then we broadcast that to our XM Pro app, which you can see on the bottom right. Next slide, please. So next, we're going to talk about the technology architecture, and this is the capabilities needed and the applications that are going to enable us to do so. Next slide. So you can see on the left side, this is our technologies capability assessment. We had the freight traffic flow analysis, storm impact forecasting, and network disruption. Those are capabilities that were core to this project. And as you can see, those are the different data sources on the top and enabling applications. And based on this assessment, we could, you can see the green check marks. That signals that we have all the capabilities that we need of the data sources provided. Next slide, please. And this is the current state of the technology architecture. You can see we broke it down by capabilities, software, hardware. So data storage in the current state, it was on OneDrive, it was in the cloud. So that was sufficient. But where we ran into some issues was the data transformation and data wrangling. And then ultimately, the visualization tool, which is currently GIS, which could have been sufficient, but it did not have the data processing and data contextualization tools that we needed. So as you can see in our future state, next slide. In our future state, we added these capabilities, which also came from our periodic table. So you can see we added data transformation, contextualization, AI, and then obviously the recommendations. And we did that. The second row down, you can see we utilized OneDrive as a storage because it was cloud-based, it was suffice. We brought that into the data designer, which was XM Pro, which is the image that you saw in the information architecture. And that was our data pipeline, which ultimately fed our AI recommendation tool. And that recommendation tool fed our visualization, and which we'll demonstrate at the end so you can kind of conceptualize this a little bit better. And as you can see, we shifted from some on-prem storage to all cloud. So this obviously enabled a lot more efficiency and redundancy across the system. Next slide. And to kind of boil this down into one slide, these are the assessments that we perform with data, technology, application, and business. And I'm not going to read through each one of these, but you can see our target, ultimately was that integrated real-time ecosystem. And then our recommendations on the right side. So everything that Jason and myself went through was kind of consolidated into this one slide. And I'll pass it over to the next person here to talk about the results.
Thank you, Mike. I will take it from here. So for the results, I was going to show, hopefully this works. Because I'm sharing my screen, I can't seem to click the play button. There we go. So this is our data stream that we ended up coming up with. This is just showing integrity check, everything's working. Mike pretty much did most of the explanation on what our sources are. I guess just some things to add, like for the WIM context, for example, that is information that comes from the website. There is an API available, but it's all private. So we kind of took information based off of that website and what our industry partner provided to us. And that's how we were able to make that section of our data stream. Moving on to our recommendation alerts, a couple of things to think about. One ask was to look at the gross vehicle weight. The weight we provided is what's considered full weight for a truck for freight. So that's what we have incorporated in there as a rule. And then because there's no hurricanes right now, in order to make sure that our data stream application is working, we ended up making other rules. So for example, like here's a rip current warning that will be triggering alerts to see how it works. If there's a hurricane, it should also pop up in our alerts and recommendations here, which is in our application. And what we decided to include is vehicle speed or WIM stations that are named. So they're provided to us via coordinates, and we basically aggregated the data in order to provide more context about where this is. We have gross vehicle weight per WIM station. And then down here is a map that updates live using, I think I ended up using Azure, potentially. But yeah, this is our application. And then you click on the recommendation. From our rules, it provides recommendations and all the information related to the WIM station that the alert is pinging from. Yeah, that's about the application. So then if I can pass it back to James to go over our roadmap.
So for the roadmap, we look at a 3-year plan to execute this digital twin and scale it up to various fleet industries to use. Next slide. So it's a 36-month or 3-year plan. For the first phase, we're looking at partnership and foundation, where we'll be negotiating with the DOT, FDOT, to get access to their WIM real-time data in order to reduce the cost of deploying other sensors, which is the other plan in case the partnership is not able to go through. Then the next one will be the live digital twin core, where we will look at streaming the real-time DOT WIM data and integrate the NOAA weather alerts and also deploy our GIS overlay to help with giving geospatial insights to the users. The next phase will be the AI prediction and modeling, where we'll look at training AI models and also helping to simulate what-if scenarios for various possible situations. And the final phase will be to scale, validate, and operate. We'll look at scaling up the platform to encompass massive data and also increase the long-term training and governance framework. So with this 3-year plan, we'll be able to help various freight companies and also the DOT to be able to make informed decisions and look at how the networks are disrupted and able to recover and optimize these supply chain routes in order to help make the Florida freight system very sufficient and very resilient. Thank you very much.
Thank you very much. Any question from audience? Okay, so I have some questions. First of all, what type of GIS data you used in this project?
So we weren't able to pipe that in. We were trying to connect it into this application, but due to some permissions, unable to. But utilizing, geospatial tools, so that helped us with the WIM stations, identifying the cities, the road network, and that was it at this point. But we have, there's definitely plans to integrate that more, but we hit a bit of a roadblock with some API permissions to really explore that further.
Okay, so in terms of the data contextualization, what type of contextualization you have done for the data in Exampro?
So for the contextualization, we brought in the WIM station and data, which is actually from the Federal Highway Administration. It gives the longitudes, latitudes, and the station IDs of all the various WIM stations in Florida, which is our case study. And also we brought in contextual data, real-time NOAA alerts that we tapped straight from the NWS, where it brings in the real-time alerts. So for the various meteorological alerts that are happening, we skewed it down to Florida specifically because Florida was our use case. So the data that is coming here is mainly for Florida, and the various stations that send in the alert, we are able to bring it into this platform. So those serve that are contextual providers to our simulated WIM real-time data. So along the pipeline, various data transformation processes were undertaken in order to enrich and bring a final form that we pushed into our app designer.
Okay. So in terms of the alerts that you generated, how did you validated those alerts?
I can take that one. So for the alert section of it, validation came from we actually made like several separate data streams prior to combining everything. So at first we really just used the real-time NOAA data and compare that to actual weather alerts that were coming in, and that's how we were able to validate this is actually what's happening from the NOAA API. So, like for example, we're not able really to test the hurricane warning until an actual hurricane comes, but I feel pretty confident that due to our testing using the NOAA API by containing keywords, that if something happens, we'll be able to see it.
Okay. All right. Thank you very much.
Thank you.
I have a question.
Here's a question, Ahmed. Yes, go ahead.
Yeah, in slide 5, you mentioned that you used the data-driven approach, data-driven approach. Can you just please let me know why did you choose data-driven, or like what made you decide that you need to solve this problem with data-driven, data-driven? Why not physics-based or a hybrid approach?
Okay, I'll take that one. So we used mainly a data-driven approach because this project is looking at how we are able to help give information and insights on how the freight network in Florida is able to recover during disruption or extreme weather events. So we chose the data-driven approach because in this process, we need like the hurricane alerts. The hurricane alerts are very important and they are all, it's readily available. A physics-based model for that one will not be the best way to go with it. So we infuse that into our system using the API from NWS. The next important data we needed was the GIS or geospatial data, which is also best form is the data part because we didn't see a possibility of modeling that with physics because it's readily available. And also physics-based models are computationally expensive. It takes a bit of some time. And this has to be very real time because in the case of extreme weather events, you have to be quick with getting the information, getting the insights, and being able to execute. The next data too is the freight data, which is already being tapped by the DOT. It's also readily available. So since we didn't have the chance to have that, we used Exampro's capability of simulating a data stream based on the real world scenario. So that is why we went in for the data-driven approach because everything here is sitting on the data-driven style. Thank you.
Thank you.
Thank you. Okay, so Michael, you're free to go. And
Thank you.
thank you, group. I appreciate your work. Make sure you upload your presentation on the web course. Okay, so group C, Ezequiel, and Sophia. I know that this is going to be difficult for you guys to talk about this whole project in 10 minutes, but don't worry, we ask some more questions. We want to be fair with others to have 5 minutes presentation, but we ask some more questions. Don't worry at all.
Gotcha. Sounds good. I'll screen share now. And make sure I'm on the correct slide as we start. There we go. All right, I'll give everybody a couple seconds to be able to see. Can everybody see?
Yes.
Okay, wonderful. So, start my stopwatch. Our project is a digital twin for humanitarian logistics. Our use case here, here's our content overview. Our use case here is for Hurricane Melissa. So Hurricane Melissa was a Category 5 hurricane that hit Jamaica in October 2025. It was a very large storm. It caused a lot of damage and also had a massive human cost. I have some of the statistics up on screen here. So the disaster response began before the hurricane actually landed in Jamaica. You had planning between the Jamaican authorities, between international organizations like UN-backed organizations and other NGOs that were not UN-backed but were still trying to help. You had all these groups coming together. They were using several different data sources together to do preemptive planning for how this storm is going to be handled. You had the initial disaster response less than 48 hours after the impact had happened and the storm had left. And we had a discussion with a panel of experts who were either on the ground or providing support. And what we heard from them is that they had varying capabilities. Some had access to cargo freight, some had access to helicopters, some had access to boats, some had none of these things. And we also saw teams with varying levels of informational capabilities. So some had a network of like churches who were able to provide them local intelligence. Some had satellite data and imagery that they were able to distribute to everyone. And the actual national response lasted much, much longer, a protracted response due to the severity of damage. So our question was really, how can we use a digital twin to improve the situation? And more specifically, we decided to focus down on logistics network monitoring and coordination between organizations to sort of improve this network response. So here we have some details on our damage assessment. I'm not going to go over all of this. Feel free, if you're watching back on recording, to pause and kind of look over what we're talking about. But the summary on these 3 slides is the sort of process, the humanitarian logistics process, is basic leaning towards developing. You see some people using informational technology, as you can see here in the route planning and the coordination protocols. You see people talking over phone, talking over SMS, and we do have some very interesting dashboards that are sort of coming into their own, but they're not really fully integrated into the process, and they're not used by all teams. And we do see a lot of different types of data, and we do see some teams that exist solely for collecting and distributing data. But this data it has varying levels of reliability, and it's not really preemptively set up to capture the state before the storm and the state during the storm, especially at the ground level. You see a lot more satellite imagery in SAR. So moving into our digital twin on our quest for change, the kinds of data that we would like to see collected is, so for our static data, we want geographic data, GIS, satellite imagery. We need to know the locations of different ports and movement protocol, like areas of movement, roads and waterways. And we want to know the throughputs of all of these things. And also different aerodromes, like small fields where you can, land a small airplane or a helicopter. And for the dynamic data, it's a lot more complicated because you're going into these areas that have significant damage. So one of the big things that we want to recommend is Starlink. We heard from our panel that this was a very important technology to maintain internet connection and distribute internet connection across these really damaged areas. But we also want to look at status reports from people on the ground. We want throughput sensors. So this would be very case dependent, but we want to put throughput sensors at the airports and the ports, and also make sure that they are deployed at different roads, maybe battery powered and motion activated sensors. The big problem is that we need internet access, we need power, and without that, the sensors are worthless. So we want to have systems that aren't necessarily grid dependent. Here's our BPMN. At the top, you can see infrastructure. This is just sort of static sensors that we can measure what's happening on the ground. At the very bottom, you can see civilian. We want to give civilians a place to report what's happening to them. For our digital twin, we're ingesting and compiling and anonymizing our data. Then we're identifying changes from our last state. We're going to update our internal map, push that update to a server dashboard, and then dispatch it to all of our people on the ground. And until they receive that update, they'll still be able to use old versions. But as soon as they get internet access, they want to be able to use those new versions to plan and route and actually distribute aid. Ezekiel.
Thank you, Sophie. So during the design phase, we focus on using the periodic table, right? Capabilities periodic table from the Digital Twin Consortium. Digital Twin that we present, it is data driven. So that's why we have a big focus, we see on the left with the data services to get the data from different data sources. Data is coming at different speeds, different formats. We are doing a normalization of the data, aggregating all that data and making sure that that happens in real time. Then we expose integration through a standard API services for integration with NGOs, third-party systems. And on the intelligence side, we start with notifications to move forward with prediction and prescriptive recommendations later. Those are some of the most important capabilities that we're looking for. And all of that being presented in an interactive dashboard that is being updated in real time. We also have two more capabilities that are important for this, for the scope of the project, that is about the privacy, compliance, and the data governance. So we want to make sure that we are in line with all the compliance regulations on the different areas, different countries, if this goes deploy beyond Jamaica, and also make sure what happened with the data that we receive, right, from those external entities. So control the access to the data, make sure that nothing there gets leaked. Next. On the data architecture side, so we are thinking on a 4-layer architecture. The first box on the very top, next. It's based on the inputs. So we receive CSV static data. We receive live traffic data coming from the TomTom API, and field reports that is crowdsourced data from the UShahidi platform. That is an open source platform for natural disasters, where people can report data from SMS, email, the website, Twitter or X, social networks, etc. The data gets into a system. We process and ingest the data through XMPro data streams. We can get data from all kind of different sources, including static files, web databases, cloud services, etc. And that's the layer where we process and we prepare the data to be used for a digital twin. On the next layer, we model the network. During the proof of concept, we didn't have that layer. It was on the fly, right? It was in memory inside the XMPro platform. But for a production grade, we need to model and we need to persist the state of the road network. That's the purpose of that layer. And then we, on the intelligence side, we are doing the recommendation system through XMPro recommendation. There's a rule-based, event-driven platform that connects with the data stream. So as soon as we get new data in the data stream, that data goes through a rule-based system and can provide recommendations to the users, and all being presented in a dashboard implemented with XMPro App Designer and with some tweaks to get an enhance on how the map is being presented using the leaflet JavaScript library. Next. The proof of concept we can see in the background on the right, that is the design phase of the data stream. And on the front side, we can see one of the views from the UShahidi platform. There is a self-hosted or that you can host yourself, or can use one that is already hosted by them. So that's the flavor that we are using. For the proof of concept, we are using a lot of synthetic data in CSV files to model the nodes of the network, the event disruptions that are happening, but we also have real-time data. On the real-time data, we have the TomTom API to receive live traffic data in Jamaica, and as well, we have integration, real-time integration with UShahidi. And for that, we develop a web service to connect the two components there. Next. This is what the dashboard looks like. On the very top, we have some metrics. On the bottom left, that map that is implemented using feature in X Pro that's called MetaBlock, allows you to develop any kind of widget using HTML, CSS, JavaScript. Dashboard is interactive. You can click the edges, you can click the nodes, you get more information, and it connected to the live stream from the data streams. And on the right, we see also the recommendations being updated. Next. We define some key performance factors that we would like to see to validate the digital twin. Those are the predictive accuracy, data integration, operational efficiency, and adaptability. And those key factors, we want to use them to understand if the twin is accurate, right? Is what we were expecting, is it solving the problem, but we also, it will be interesting to see and connect with KPIs that coming from the humanitarian logistics operation. So the real ones, that the one that they're using in the day to day. We don't have the data for that today. That's what it's called future KPIs. So, but it will be interesting to see how they change before and after the implementation of a digital twin. Next. And for the roadmap, on the first year, we're going to implement what we saw in the prototype, the map, the live data stream coming from Ushahidi TomTom API, but now in a production grade situation here. On the year 2, we want to enhance that implementation, adding more data sources, satellite, weather data, implement logistics, inventory integration. That means, for example, if we receive donations, we want to know, okay, which donations, of what type, where are these donations coming from, and when, and also we want to understand where we need to distribute those donations. So that is the inventory and logistic working together. We also want to expose in year 2 a public API for better integration with external third-party systems. And in the year 3, we want to expand and implement more automation. So we want to add IoT sensors in the island in Jamaica that can be connected to a digital twin. We can implement autonomous rerouting for prescriptive recommendations, and we want to expand out of Jamaica, maybe to some other countries in the Caribbean. Next.
And we can skip over this. We've already talked about all this stuff. And here is our, we wanted to thank our industry partner and our panelists for all the help they've given us. And here's our sources. We can take questions now.
Thank you very much. I mean, with your panel, with that extensive panel, I think you have a good plan for future, because I know that they were asking a lot of the different questions. Okay, so back to the sensor that you mentioned. What type of sensor you are provisioning for this type of model?
The primary type of sensors we would probably like to see is essentially like trail cameras. So you get battery-powered motion detecting trail cameras that either teams can deploy before the disaster response or during it. So before the storm hits or during the storm. And you just set these up on a road, or you set these up in an airport or any aerodrome or any port. And you just want to point them at where you expect like movement to happen, so that you can keep track of like how many people are passing through these routes, and you can keep track of like, is there a blockage here? Do we have a lot of people trying to go down this way and then ending up having to come back later? Or is there just complete stoppage, so there's like a pile up of cars, that kind of thing?
Yeah, so what is the protocol for integrating that sensor into the platform?
Do you want to talk about that, Ezekiel?
It will be, so yes, we can receive live stream, right? From, if we have cameras, receive live stream data. But basically that will be the protocol. Some other sensors can be integrated with web technology, MQTT, etc.
And
Yeah.
probably interpret the visual data through just AI descriptions and then pull out
Can
the
be
statistics.
So what type of AI can be used for that sensor, for that camera imagery?
Should be what's the word for it? Digital vision or machine vision algorithms to detect movement and detect what exactly is going through that area. and then interpret the, like, just essentially count up the number of cars over X amount of time, and then have that as an integer statistic.
Some classification.
Yeah,
Machine
classification
learning
machine
applied
learning.
that can be applied on the edge, probably, so we don't have
Okay.
large amount of data flowing into the twin, but that gets processed locally, and then we just receive a small piece of data that is telling us about, okay, what are the things that are happening right in that location.
Okay. And in terms of this whole project, I think one of the issues that you mentioned is about the data governance and the sensitivity, security, and trustworthiness. So, what framework you think that can be used for the security and trustworthiness?
I actually had this on a slide that we weren't able to cover. But one of the most important things I think is sort of compartmentalizing the system between nations. So if you have the system running in Jamaica, then it should be running on servers that are controlled by the Jamaican government, and they should be able to give access to the system to all of the NGOs operating in their territory and have control over it. And the NGOs, when they're sending off their data, one of the important things that we want to happen is that the data is anonymized as it's going in, so you can't see like, oh yeah, Samaritan's Purse is the person who is giving, or is the group that's giving this community report. Because then you might be able to sort of figure out exactly what kind of community members are giving the report, or how they're connected to Samaritan's Purse. Like you don't want to give that sort of information. You just want to give the community report itself. And also in terms of the teams on the ground, you might want to delay that data by maybe an hour, maybe 30 minutes, depending on the sensitivity of the data for security. So you don't want to have like a live feed of roads just available to any of the other NGOs, because then if you have a data breach, then they could just go to that location and, watch the live stream, and there might be like security issues with knowing exactly where somebody is at any given point in time. So if you have just a short time delay, you can prevent a lot of the predictive power for anybody who's, trying to use that data for nefarious means. And the third thing is limiting the system to whoever, the nation approves of. So the fact that the nation has to approve of a group for them to have access gives a lot of security that the NGOs can trust that their data isn't just publicly available to anyone who might want to exploit it.
Is there any standard that you can mention about the security?
Ezekiel, you'll be better informed on
I'm
that than me.
thinking, yeah, I'm thinking on some of the security standard that maybe from here we have the NIST framework, right? For example,
Yeah.
853, 80171.
Yeah.
We need to take a look at that, but those can be like a good starting point to make sure that we are in compliance with the data. Another one that is pretty common here is the CMMC, Capability Maturity Model. But usually what we see with the different security standards, that in the end, you need to report. And for reporting, everyone wants to see how whatever framework or standard you're following, how they map into a NIST framework that is well known, and you can compare against others. So I will start from there.
Yeah. Thank you for that. Ahmed?
Yeah, thank you for this presentation. Can you please go to the roadmap? 1 second. Okay, so my question is like, how would you measure the success of this digital twin, like once deployed, and like what type of KPIs you would track to see like the performance of the success of this digital twin?
Sophie, can we go one? Sorry, thank you for the question. Can we go once? Yeah, right there. So that's what we are thinking. So following the material right from the class, the last module. So we learned about these 5 KPIs: predictive accuracy, data integration, operation efficiency, adaptability, and cost. I dropped cost from that list because we believe that the cost of the operation is or for the digital twin itself is going to be hard to measure because we cannot understand and we're not going to get the data exactly of what is the cost of the operation for all the different moving parts, all the different NGOs that are participating here. So that's going to be something that they can do by themselves. But what we can do, we can understand, for example, if the twin matching the reality, if we if we see a find a disruption in the digital twin, is that also happening in the real world? That is one of the metrics for the first one. For the first one. On the data integration piece, are we in sync? How long takes the data? When something happens in the real life? So how many minutes? How many seconds? What is the time? What is the lag uh, for to get that data that is coming from different data sources? On the operational efficiency, we can measure, for example, how the mean time to recommendation. So how long it takes for the twin to provide a recommendation in minutes after an event happened. And on the adaptability side, for example, we can measure how long it was going to take to implement maybe a new data feed. You want to expand the scope of the digital twin, maybe like in year 2, right? Like we're planning to add satellite images, weather, maybe the data, or year 3 with the IoT sensors. Okay, but how long is it going to take to expand and make sure that the digital twin is going to adapt, right, to these new requirements and new data that's going to integrate it with the existing data. Those are some of the main, the 4 KPIs and some of the main metrics. We can define more metrics. We just put like a 1 for each as an example.
Yeah,
I don't know if
that's
that
nice.
answers the question.
Yeah, thank you.
Welcome.
Any other questions? Okay, if not, thank you very much, team. I appreciate that.
Thank you
And
very much for your time.
Thank you.
I hope that you can actually submit this report to the industry partner as well for everyone who already done that.
Oh yeah, I have all their emails ready already. I'm going to make sure to send it to everyone.
Yeah. Thank you. So next group is group B, Thorsten, Safura, Nakia, and Abdel Kader.
Okay. Hello, everyone. We means Thorsten, Abdul, Nakia, and I chose our project with the name Digital Twin Tour Guide for Orlando Leisure Travelers. This project is within the course case that was digital twins for modeling economic impact in urban environments, and we chose tourism because how people move around or choose activities or react to the changing conditions really shape their experience in the city, and also the experience that we had ourselves and our team members with their families. We didn't want to build another trip plan because we have already enough, but we instead wanted to see if we could create something that is more dynamic, something that actually helps traveler to make real-time decision during the trip, not just before that. So we focused on real-world factors that affect their trip daily, like weather and traffic, because both of these can quickly change your plan. They can also make it even stop or not enjoyable. Excuse me. Oh, okay. So in this presentation, we will talk about our problems and objectives. We will explain the data and methods. We will go through the architecture that we designed. Then we will show you the process and solution workflow. We will share how we validated it with Exam Pro, and finally, we will end with the roadmap. So overall, we are trying to show you that how we moved from the current disconnected tourism tools to one system that actually understands the context and can suggest better next step for the traveler. Now, why this matters? Because the current tourism planning doesn't handle change very well. So most tools give the plan to the traveler, but they don't adjust if anything changes. So traveler needs to switch between apps like maps, weather, traffic, or booking, or different things, and basically they are handling everything by themselves. In a place that like Orlando, these things become like a real issue. Like if it's a rainy day or traffic, it can change the plan completely. So our goal was to design a digital twin tour guide that combines itinerary data with weather and traffic and gives a clear recommendation to the traveler so they can adjust it in real time. In a simple term, right now the experience is static and fragmented, and we wanted it to make it adaptive and connected. So for this project, we kept the scope manageable, and we focused on a 7-day Orlando itinerary with weather and traffic inputs, recommendation rules, and a simple monitoring dashboard. And from there, we will show you how we built that idea into an actual architecture and workflow.
So to talk more about our methodology, our approach to this, we started out with interviewing industry leaders. We talked to Orlando Regional, Visit Orlando, and also academic professors to get an understanding of what data or what applications or digital twins that are out there in the market. The most of the feedback that we got is that that data is not there in the fashion that we wanted to use it. So with that understanding that drove us to look at literature, a couple of literature documents to kind of understand what is currently being studied and reviewed. As you see there, we looked at the potentials of digital twin for analyzing travelers' behaviors and also to look at extended virtual reality. Those two documents kind of just showed us that hey, there's a lot of applications that could be used for tourism, but not one exactly like we were trying to make. So the idea that we had was still pretty innovative in a sense. So we also was able to evaluate existing tools that was currently in the market, which was the AI traveling trip planner, weather app, travel app, the common applications or tools that we use to evaluate. The prototyping of the data source, again, we use like um, CVS type data to explain our itinerary, and we look to use the weather app and TomTom for our transportation and also XM Pro implementation to kind of display our prototype and what we wanted to do. Next slide. So looking at all the content that we did and talked to industry leaders, we identified 5 areas that were like the gaps. One was the data integration. As you know, that there's multiple tools that one traveler must use. So our idea is to, in the future, is to unify those, at least those 3, which is the itinerary, the weather, and the traffic, and some form of feedback. Next was the decision making. All of the decision making once a traveler plans to interrupt it is reactive. In the future, we wanted it to be a data-driven type of an approach for the traveler experience. The responsiveness of the information is pretty static. We would like for it to be real time and adapted to the changes that is real time happening with the traveler as they experience their day. User experiences, again, to move from a multiple tools to a single source tool, like a simple app that they can use. And as far as intelligence goes, is right now is the AI aspect of just planning, but with the digital twin, we want to incorporate the planning along with predictive activities, predictive capabilities with this tool. Next slide. So we just put together a business process model that would show the experience that a traveler would have. On the left-hand side there, you see a column for the traveler. In the middle, the interface that it would have with the digital twin, and then on the right-hand side, you would see what is happening with the external data. So the idea is that the customer or the traveler will open up their app and input the data that they need for their travels and their preferences. And that information will get fed to the digital twin. And at the same time, the weather and the traffic information is being analyzed by the twin and providing a recommendation as to what the the traveler will is experienced with the data from the external, and provide them recommendations if the weather or the traffic becomes outside of the preference or the range of the traveler, and that will alert them, and the traveler will have an opportunity to either accept or reject that recommendation. So that is the idea that we have set forth.
Yeah, so on this slide, we show how the information system for our digital twin tour guide transforms the travel experience by integrating multiple data sources into a unified context-aware platform. Currently, the travelers rely on separate consumer apps for itinerary planning, the weather update, traffic information. It requires manual interpretation and constant switching. So our system here streamlines this by connecting key data inputs. So we ingest the itinerary data from CSV files. Open Meteo supplies real-time weather update. TomTom application or routing API provides live traffic and route information. And we include backup activity for dynamic replanning. So these inputs are aligned to a context layer that cleans up and standards the data, such as date, time, formatting, and location matching, so to ensure seamless integration. From there, the decision layer applies business rules based on weather condition, traffic threshold, alternative activities option to generate recommendations. Finally, the application layer presents these insights to the traveler through a combined interface, feature, calendar, recommendation feeds, activity tables, and interactive map. So by moving from isolated tools to a single context-aware information system, we enable continuous monitoring and real-time recommendation. So that way we enhance the usability and decision-making for leisure travelers. Next slide. So here we highlight the key technology components we selected to build this digital twin tour guide prototype and why they were chosen. So first, we use Open Meteo for weather data, right? It provides relevant forecasts, a variable like time, rain, weather, temperature, and precipitation probability. So this is essential for understanding dynamic weather impact on activities. Next, the TomTom routing API, which was very useful, delivers the live traffic data around summary between the origin and destination locations. This helps us capture real-time travel delays and congestions. So our core streaming engine is XM Pro, right? Which handle the continuous pipeline for filtering, join multiple data sets, performing calculation, running recommendation rules, and integrating results into a visual dashboard. The travel dashboard and the map interface then present a unified view of the itinerary, recommendation activity, the activity lists, which is we had hard time to show, and route information, offering seamless user experience. Our current limitation, one more thing in that slide back. So one current limitation is to notice that TomTom live traffic data is integrated using a threshold based on alert system. One of the things that we look in the future is predictive future traffic routing remains part of our roadmap for future development. Now, next slide, talking about the roadmap, right? So before we go to, and show you the proof of concept that Todd is gonna talk about next, we want to give you an idea about the 3-year roadmap to evolve our digital twin tour guide from the current proof of concept prototype into a fully predictive and scalable platform. So phase 1, proof of concept foundation, this is where we're at now. In the first year, we focus on creating a solid foundation by aligning schemas for itinerary, weather, traffic data. So we developed the XM Pro filtering, joining, recommendation rules to process and contextualize these data inputs. We built a dashboard and map prototype to provide the traveler with the unified monitoring interface. We also tested critical scenarios like rainy days and congestion to demonstrate practical value. Next, so phase 2 is the adaptive live integration. So now that in the second year, we're planning to replace any simulated inputs with API feeds whenever possible. We'll expand the itinerary adaptation to be richer and more flexible. The usability improvement are targeted through better explanation text and enhanced feedback capture to improve the traveler's experience. Phase 3, predictive scaling. So that's the next level. By the third year, we aim to add predictive features, including future time traffic and disruption forecasting. We'll integrate richer contextual data, such as point of interest, booking, and event information. Government privacy and performance monitoring will be strengthened to support reliable, scalable operation. And now I'll let Thurston to give you a tour of our proof of concept.
Yes, and this is the technical core of our prototype, the workflow that turns different data sources into a concrete travel recommendation. The important point here is not only that data is collected, but that it is processed, linked, and made usable step by step in XM Pro. First, the travel data is standardized. That means time information, location, and coordinates are prepared in a uniform format so they can be used consistently. Then weather data is filtered according to the respective trip or activity and linked to the travel plan. In this way, a connection is created between what the tourist wants to do and the current environmental conditions. In the next step, traffic information is added. Through TomTom routes, travel times, and possible delays are integrated. This allows the system not only to see where someone wants to go, but also to estimate how long the trip will realistically take. This combination of contextual data is exactly what makes the difference between a simple app and a digital twin. Finally, the alternative activities, what is marked with the number 4 here, are added, and the recommendation is executed in the system. The crucial point is that the platform does not stop at analysis, but directly generates a usable recommendation for the traveler. This shows that our prototype covers the key digital twin functions, capturing data, contextualizing, integrating, calculating, and even translating it into an action. Here you can see concrete recommendations are generated from the current context. In the prototype, we have mainly implemented 2 types of rules, weather-related recommendations and a traffic-related reaction. With the weather rules, the system works with the type of activity. If a planned activity takes place outdoors and rain probability or rain exceeds a certain threshold, the system suggests alternative indoor activities. This makes sense because the user does not just receive a warning, but directly gets a particular alternative. If the activity is already indoor, the recommendation is different. In that case, the system indicates that the plan remains feasible despite the rain. This makes it clear that the system does not only react to weather data, but also takes the context of the activity into account. That is important for tourists because not every weather change has the same effect on the daily plan. For traffic, the current prototypes use a quick rule-based reaction. If the calculated travel time exceeds a certain threshold, a route change alert is triggered. What here the threshold set is 1,200 seconds. This is not yet a fully predictive routing logic, but it is a working first step toward dynamic traffic support. So we can honestly say that weather recommendations and traffic logic are already present, but the traffic function is currently more reactive than predictive. The final slide, that one, is meant to clearly classify the current state of the prototype. Our goal was to give the traveler one central place where calendar context, activity context, recommendations, and special information can all be seen together instead of switching between multiple tools. In the current version, the weather feedback is already visibly working in the video. Is it running? Safura, can you please make sure that the video is running? Thank you. So it will provide constantly recommendations. This is just the recommendation side. Afterwards, we can take a look at the application side, which is coming up here. So the map and calendar context are also recognizable in the application, and the recommendation output is generally integrated. It shows us that the core idea is not only described theoretically, but already exists in a functioning prototype.
Before you mute.
Okay, you hear me now?
Yes.
Okay. So finally, we wrap up with these three takeaways that we have. This project matters because it shifts from itinerary planning from something static into something that actually supports decision in real time. And second, our prototype shows that we can bring everything together, like itinerary data, weather, traffic, alternative activities, and recommendation logic into one working pipeline by ExamPro. And the last one is that weather recommendation works well, traffic included as a rule-based alert. And at the end, we still need to work on our prediction for the next step because it's not implemented yet. And overall, we built this as a solid first version of a tourism digital twin. And it shows a clear path forward for having advanced predictive tool for traveling. Thank you for listening to us, and the floor is open for your question.
Thank you very much. Any questions from others?
This is Jordan. Yes, I have a few questions to think about. All right, so what would be necessary, do you think, to turn this XM prototype into a usable application? How could you measure the benefits of the application? From your research, are there any other data sources that you would like to have that you were not able to get access to this semester? And would you have like a recommended workflow for leveraging any existing planning tools and integrating them with this application?
Yeah, I'll take some of that and I'll let my teammate to contribute. So one of the things that for the XM Pro is like we would like to get the full version of XM Pro because this is a class, so we didn't have all the capabilities of the XM Pro. So we'd like to have the full capability, especially when it comes to debugging. In terms of the data, yeah, we need to get more data like we use in TopSum, but it's limited use and the weather. So we need to look at some other data stream to give us not better, but is current data. The benefit is the users, right? So we make sure that we get some tests with some travelers using the application and get feedback, and then build on top of that. So that's, I'm gonna let my teammate to add to this if they have any other.
Yeah, I guess I just want to add the last part you mentioned. The most important thing is really getting out, getting in contact with the stakeholders. What are actually the users? Of course, it could be my family, but just to get insights of making that really usable, understandable for the human computer interaction point of view, that it is not just a tool that gives you predictions, but really people need to use that. I'm thinking of having a smartphone that sends you alerts, hundreds each day. I do not know, but if there is another one that will kind of um, um, runs in the dark because there's so many recommendations. It should be a proof of concept created with the stakeholders. Yeah.
Yes, and also to add on to that, and you asked about the data sources. Like one of the things we definitely want to be able to do is have that itinerary plan. Right now we have that CVS file, but we would like to actually have a API with the actual itinerary plan. That's one data source that we would like to future to put in our future model. The next is that predictive aspect of the routes. That's another aspect of this that we would like to put in. As far as the metrics aspect of this is looking at the response time of the digital twin, if there's any lag within the data or any lag within the notifications to be able to fix that. So, and also making sure that it is a real-time response to the user. Another piece of this that we had thought about it was that actually having the personal aspect or the personal health of the traveler also inputted in this. But that is one piece that we had limited to, we didn't have a lot of time to fully explore. So the person health condition could be something else that can influence the change for this digital twin. So those are some additional things that could be explored with this.
Yeah, plus the booking and other stuff that a traveler need, like from the beginning till the end. If you could have like all those kind of data and match everything together, it would become like a perfect thing. But it's as we have the plan for 3 years, it would be something step by step and growing by the time.
Okay, thanks. Good job.
Thank you for the question. So I have a question regarding to the visualization. So besides this 2D or 3D, even 3D map, what type of other visualization do you envision for this type of platform?
So I'll start. So one of the things I was thinking about to add is like you saw the calendar, right? And we had the activities. So once you click on that day, it show you the activities. It gives you green, red, yellow based on the weather and based on the traffic. Also, the activities give you some indication about the state of your activities. This box here, right there on the left side.
Okay. And then in terms of the validation, because your platform has got a lot of data coming together, what method of validation do you think is applicable here based on your understanding or learning in the frameworks of validation or mathematical application here, so that you will understand what is the level of error when you generate some data out of the real-time data, and then contextualize that and connect that together and move forward.
One of the things that comes in mind right now in terms of validation is demonstration, right? So have this application installed in one of the, either iPhone or Samsung, and have a user go into the field and then walk through, and then we can track them and see, how updated we get the feedback into the application. I think that's one of the things that I'm thinking is to demonstrate, test by demonstration.
Any other idea from the other team members?
Yeah, kind of integrate a survey-based validation where we actually can try to use the feedback of the stakeholder again, because this is mainly, it's a wicked problem because this is very adaptive and very intuitive and very specific to whatever person uses that. So for me, I would definitely go validating the output and the data by using survey-based validation to create content that is really valid to users. That is what the application is made for.
And then in terms of the AI ML, in AI ML, we discussed about several types of digital twin, and it seems that you are talking about the predictive aspect or predictive digital twin. So if it wants to be a reactive digital twin, what would be the capability that you will add to this to make it a reactive digital twin so that it can support the decision maker for their future plan?
So I can explain a little. Sorry.
You mean reactive or proactive?
Reactive.
So I lost my thought.
So one thing that I'm, having my thought is in terms of the traffic and congestion, right? So if we have an AI prediction that can capture historic data and also tap into other, databases from Google and Bing and routing, and train that model to look for congestion, right? So and then deploy it and predict future congestion instead of right now we have a threshold, but in the future we'll be able to predict future congestion based on what the AI learned.
Okay.
And
Thank you.
yeah, and I would add to that is the weather aspect of it, to have that like 7-day forecast already projected in to or projected onto the schedule, so that will give the traveler information ahead of time on how to adjust their itinerary. So having that forecast in place, that will also be a benefit.
So yeah, just to give you I mean, not to be confused with the analytics. We have analytics, prescriptive analytics, and so on and so forth. But reactive, as Abdel and also Nakia mentioned, is about the assessing the current and future situation so that it can assess and then give some reasoning so that the user can make a decision. And I believe that this is very important in your case, because the user is always facing unexpected behavior of the weather, the traffic, or anything like that. So the system should be reactive, not predictive. It should be predictive, but the reactiveness is very important. So that's one dimension that you can consider. And also another question is about the real-time simulation, because your system seems to have to should be able to run the real-time simulation. So is what type of real-time simulation you are envisioning in this type of system?
As I get your question right now, the data stream is configured to itinerary pull the data every 10 seconds just to create content that we can show that there is something going on. The idea here is for especially the reactive part is to change that to real-time data that we can, as we start that application and the data stream, it will have frequently looking at the data set. And for that, we are going to switch from CSV data sets to real-time API connections to a weather data set that is really the asking for the current weather. and having then a frequently recapture of what is the traffic looking like, what is the weather conditions for that specific situation we are dealing with as a traveler. If that answers your question.
Partially.
Which part I missed?
Yeah, I'm talking about what type of real-time simulation scenario you can consider here, right? So you are saying that, but make the assumption of the population. You need to generate the population or generate the traffic in the real time and get the real time and even go for ahead of time to be a reactive. So it should be running the simulation to give you the idea what would be the change, and
Yeah.
then bringing that back to the user.
So the sorry, go ahead.
Go ahead. So as you explain that further, Professor, one of the things that a simulation model could probably help enhance this is that it could look at the historical seasonal traffic that affects the area. So those things can be run and understand this is how the traffic changes throughout the months and seasons or months and years through in the digital twin. So that's one aspect that it could take a look at. And it could also help with understanding how if there's traffic jams, like what that impact will have, or you could simulate that also, and that can also provide some additional data.
Yeah, the historical data is very important, and combining that with the real time is certainly important. Okay, Ahmed.
Yeah, actually, I have a couple of questions. Some of them are like foundational questions. The first question is, what is like? If you remember at the beginning of the class, we discussed when we need to build or we want to build a digital twin, we want a physical system for the digital twin. So this is a foundational question. What is the physical system that you want to build the digital twin on? We discussed that the physical system is not just the physical components, it might be some processes or business processes. If you go to the PPMN that you have, my question is, what are the main business processes that you are like trying to build a digital twin for?
So I think if I understood correctly, so right now we have all the apps separately, like the if it's about the traffic and everything, we have them separate, and I think we can consider those ones as a physical aspect, and then we want to make it a digital twin that works, in real time. And every time that the traveler needs to check something or needs to be alerted about something, they could be alerted in real time.
Like, what are the business processes like in your, like, let's say, problem or in your, like, or in the industry partner that you are like in the company? What are the main business processes? And the digital twin, like, basically, like, which business process is like mostly focusing on to solve, like?
Let's see if I understand. So when we look at the process here, there's like the process for capturing, if I'm capturing it right, the process for the weather, the process for the traffic, the process for the traveler roles and responsibilities or aspect. Those are three different ones, right? So when we map those out individually, when we started just with the traveler alone, what they have to do with without the digital twin, that was a very it wasn't a it was almost like a a stop and go type of a process there. So, and then when we looked at the data separately, the data only had aspects just showing the data. Just the weather for the day, but look at the it didn't look at the travel of itinerary to kind of understand what's happening, nor did the traffic aspect of it. So it's almost like three different processes that has to be unified in order for this to actually work, if I'm answering the question.
Okay. And for the Thorsten, like he mentioned, like for the like frequency of updating the data or the digital twin, I remember he mentioned 10 seconds. Like based on what you decide like you need like 10 seconds, and why is it 10 seconds? Do we really need to update the system or the data like for the weather? Do we need really like to update the system every 10 seconds, or like
No.
will the plans like for the traveler will be changed every 10 seconds or?
No.
No. So that is just for the prototype to give him some life, to create some data we can actually provide you. The main idea when I'm going to change or to have that trigger points, and that is kind of answering the questions the professor had before. I would assume that only if you change the place. If you want to go from point A to point B because you have another stop on your trip, then of course you have to consider, okay, what is the weather? What is the weather looking for that? What is the traffic to go there? These are kind of trigger points you can use for going through that circle of checking if there is traffic ongoing. Because if I'm spending the whole day, for instance, in SeaWorld, I do not really care about the traffic on the road, especially during the day, during my stay at SeaWorld. But considering if there is a weather change, of course, that might be a trigger point to alert and start that process where we can then go through that steps and checking, okay, there is a bad weather front coming up. You want to change your plan in the evening hours. You want to go to an activity that is indoor. What is close enough? How far do you have to go there? When do you have to leave? These are all considerations we walk through. So I'm thinking of having a really up to date but not so frequent check. I would go for an hour because these are most the time you spend on specific activities. And every hour I'm going to check. And if there are any main circumstances that are changing, like weather or traffic, or even the trip is changing, you are at point A and you want to go to point B, then you have to consider the traffic and the weather changes and taking a look at that. So these 10 seconds was just there for creating content, because pointing out too, we do not have so much time in that presentation to show you more than one data test. That's why 10 seconds.
Okay, the last question is like, who are the users for your platform? So you mentioned you built a dashboard and platform. Who will be like using this dashboard? Is it like a software that you will sell to travelers, or is it like a company that they will use this dashboard, or?
Oh, traveler.
So the traveler, but also Visit Orlando. It's a company here local that can leverage this to offer to their customers, right? So that would be a good avenue to use this application.
So to also add to that, if we expand upon it, we would definitely want it to be like a personal user app, because the idea is for the traveler to put in probably some personal information, like things that are going on with them that could help that could be fed to the digital twin, that could also feed a recommendation based off that. Say the traveler is for whatever odd reason breaks a leg and something happens, and so the digital twin will be able to provide them with new options on your where to go and what to do and for what time frame. So not only could it be application for a company, but we also would like for it to be an application that non-technical traveler, a non-technical person can use, a traveler can use too. So that's probably two different audience, but that's what we would like to encompass.
Okay, that's like bring another question for me. Like when you build the system, like is the traveler, because sometimes you are saying like the digital twin will, like when something happened, it will suggest or change the plan for that traveler. Like, do you think the traveler should be always in the loop, like to make these decisions, or so the digital twin will suggest certain like changes for the plan, or it will adjust the plan automatically?
No, the human is always in the loop because it's their, not just say their itinerary, but the idea is that the digital twin will provide us recommendations, will provide them recommendation on based on the information that is being fed to it versus like fed to it from the traveler and from the weather. And it will alert the traveler and give them recommendations, but the traveler will have to decide if they want to move forward with that recommendation. I mean, so we want them to stay involved in that, in the loop.
Yeah, that's why they're included here in the business map that we have.
Thank you.
Mhm.
Okay, so marathon questions. Good job, guys. And also, I wanted to suggest and wanted to make sure to see when you are reasoning, like you are talking about the frequency of data, the users, and the I mean the type of visualization or technology that is being used for analytics, for simulation, visualization, and so on, based on the user. Make sure you have justification coming from either the technical reports, the literature, or your interview. So it should be coming with justification on that. All right. So we can brainstorm like every hour, for example, is enough. But let's get that justified through the literature or your interview with the client. Where this is coming from is very important. Okay, thank you very much. Last but not least, we have Group A on seismic prediction for seismic radiological emergency preparedness and response. You can start when you're ready.
Yeah, thank you. So we're excited to share our digital twin project for seismic radiological emergency preparedness and response. So this is a project that we did with Kosti, Alfredo, and myself. The primary problem that we were
Sorry,
getting.
Amy. Sorry to interrupt. Can you go to full screen?
I thought I was. That's weird.
Maybe your screen.
Guess you shared the wrong screen.
What were you guys seeing?
Now is this is
Yeah.
not shared.
We
But
have seen your PowerPoint software.
Oh.
there you go. Yep.
1 second. This is not right?
It was before this, but now jump back to this.
Okay. Weird.
We're just seeing your 5 slides on the side, left side, and blank.
Okay. Could one of you maybe present instead? I'm working on my backup laptop and I guess it's not behaving.
I can share my screen.
Thank you.
Oh, is it clear?
Yeah.
Perfect.
Thanks, Kosti.
Yeah.
Okay. Yeah. So digital twin for seismic radiological emergency preparedness and response. We can move on to, so the core problem that we were given to work on is that emergency response teams currently have separate systems and they lack proactive alerting in multiple languages. And what was needed is a digital twin to integrate this disconnected feeds into a cohesive and scalable view with multilingual alerting. We can move on to the next slide. So we first examined the current state, and here we have pictured a business process model and notation for a radiological emergency in its current state within the US. And we can see from this that the current state is siloed and it's a reactive state. So it starts when there's an actual emergency that's already occurred. And really, the seismic data from the USGS is the backbone data source for us throughout this project. Our target state would be to have multiple agencies that are involved in these emergencies, leveraging a common and unified system. So here we have 4 different entities working together in this BPMN, which is kind of the minimum required for an emergency situation like this. But often, if it's a more complicated emergency, there's even more agencies involved, and it becomes really important for everyone to be working together and having the same information at the same time. You can see from the BPMN that they do start to work together in later stages with those vertical boxes, but that's after some delays. And so the digital twin would be kind of bringing all that information and coordination across agencies up to the very start of the process so that they can be more effective. And information being available in multiple languages was really emphasized as a key component as well. And then we were also asked for this digital twin to have capabilities to predict earthquakes so that we're not just responding in a reactive state, but able to plan ahead. So we can move on to the next slide, Kosti. So getting into the current state information architecture, this is for radon. And the core database here is the EPA's RadNet database. They have 140 sensors across all states, and it's updated in near real time through CSV files that are saved to the EPA's website. The EPA is continuously monitoring these levels from computers, and then if they see the levels increase meaningfully, it's given to a human. EPA staff are alerted, and they investigate the cause. Unfortunately, there's no APIs available for this database, though. But when there is a potential for low concentrations of radionuclides due to either some kind of event within the US or internationally, RadNet has air filter inquiries that are logged, and this is where they kind of enhance their monitoring. Maybe they reduce their thresholds for what they will be alerted on so that they can make sure radiation levels don't get to a dangerous level. These are not responses to known radiological emergencies, and they're pretty rare. There's only been 5 in the last 10 years. So I'll pass it over to Kosti here for our next data.
So thank you. So in order to understand what is needed for our digital twin pipeline, first we need to understand what is the baseline. Amy previously talked about the data related to the radon data. I will be talking about the current state for the earthquake data. So we will go through what we have found. So what we found is that the core database for earthquake events, it is called COMCAT. And it is considered the master database for all earthquake events. It provides us with data regarding the earthquake's magnitude, regarding its depth, and regarding its location. Now, what is also very important for a digital twin is the data distribution pipelines. So what we found is that regarding the earthquakes, there are 2 types of APIs that we can use. Now, the first one, it is called the GeoJSON feeds, and that one that we will be using for our digital twin pipeline. It provides us with real-time data regarding the earthquake magnitude, depth, and the location as well. And the other one, it's the FDSN Event Web Service. Now that one, it has a higher level of complexity of metadata. It provides scientists who does statistical analysis on seismic activities, and because it actually provides them with a way to query specific, specific locations or specific magnitudes, and it has data related to waveforms and data related to the stations themselves as well. So what is also needed to understand in the current baseline is the operational products, what application the USGS provides. I have found many, but I brought two, most important two with me. So one of them is the shake map. It provides near real-time visualization of the ground motion and the shaking intensity. And the other one is the earthquake notification service, which monitors these feeds and sends an automated alerts to the emergency responders and to the public via text or email. Now, what we also found that FEMA has a role in this ecosystem. What is interesting is that FEMA has a platform that is called HAZAS, which provides the emergency responders to conduct risk assessments. What is more interesting, what we found is that we found a business flow between FEMA and USGS. Now, I previously mentioned ShakeMap that provides us with near real-time visualization of earthquake. FEMA uses those events and translate them into risks. So it provides you with, for example, ShakeMap tells you that there is a magnitude of 7. Emergency managers can conduct what if risk assessments to say that what physical damage would happen if that amount of earthquake would happen, and also regarding the economic, how much money they will lose, and also social impact, how many shelters should we put in this location, and so on. So the strategic impact of this application is that emergency managers can plan for all the disaster phases going from preparedness, response, mitigation, and recovery. So our proposed target architecture is that we will be using the data from the USGS GeoJSON feeds, and we will also use AMI's data regarding the EPA, and also Alfredo worked on the data related to the locations of the earthquake, the nuclear facilities themselves. And we will be adding an analytical module, which is the Markov chain Monte Carlo. And here in this image, we tested our Exim Pro during the project on this nuclear plant, because we have found in the articles that it is the highest risk. Here we can see it on the Michigan River. So I will hand it over to Alfredo.
Thank you, Kosti. All right, so I'll be walking you through our data architecture, our technology stack, and the working prototype that we built. The architecture that we built addresses the problem of fragmented systems. So if you look at that image on the top, you have the three distinct data streams from the USGS seismic feeds, the EPA RadNet radiation sensors, and the NRC nuclear facility operational status. And so by fusing these three streams together, we get a single shared operational picture. On the right there, there's an image of a screen. This is an automated push of notification by leveraging FEMA's integrated alert and warning system. This system immediately can translate into multiple languages, like Spanish and Polish, in addition to English, to accommodate diverse demographics in the region and help them instantly understand the evacuation orders. Next slide, Costa. All right, so for the technology architecture, here's a periodic table that we use to highlight our MVP core capabilities. On the far left, you'll see that we ingest the data with streaming and use real-time processing. The next comes the orchestration piece, where the data integration takes place. And then on the right, it gets unified into the dashboard visualization for the multi-agency emergency response teams to see. So to prove this integration out now, we did an initial prototype, and we used the XM Pro data streams and Our ultimate state goal will be to use a TOGAF aligned stack using tools like Python, Apache Kafka, and other tools that are standard for live streaming. Next slide, please. All right, so here's a data stream prototype that I talked about from XM Pro. It shows the data ingestion. The three red squares there are for the inputs from the three teams. So we successfully pulled in Costy's simulated USGS earthquake data that we created within XM Pro. Amy's EPA radon data is up on the top in the middle there. And then I pulled in the NRC nuclear facility monitoring data that we that we joined together using the regions and operational status to highlight the risk areas. And in the end, there's the single pipeline that gets joined together as from the separate feeds into a single pipeline into the XM Pro application. Next slide. All right, so this slide shows our joint data sets flowing. On the right is how our live data view from that stream harmonizes those data sets from the earthquakes, radon, and facility statuses. So it's like a continuous output feed, and then that can trigger automated safety recommendations based on the thresholds that were set. Next slide. All right, so this one shows a prototype of our emergency response dashboard. It's fed from our data stream, and the system automatically categorizes the threats based on the different categories when focused data crosses our defined parameters. So on the right, you'll see that there's split in two, and you have public safety recommendations on the top, and then the nuclear facility recommendations just below that. Next slide. All right, so in the future, we're going to enhance this visible representation. After the prototype, we're expanding in the future phases to handle more emergency areas, more live zone status, and emergency managers can interact with this dashboard, view the multilingual triage instructions, and then coordinate multi-agency response from this one single pane of glass. So I'll hand it now to Amy to show you our future deployment roadmap.
Thanks, Alfredo. Yeah, so starting off, we completed our phase one, which was our pilot. We selected that DC Cook plant that's right on Lake Michigan. It's just across the lake from Chicago, and it's literally on the lake. And it was noted by NRC, the nuclear facility regulator, as one of the more vulnerable nuclear facilities to an earthquake. And any potential damage from an earthquake. And so given that it's close to population centers and potentially could disperse across that region, we focused there. And we understood the current state, where the data is held. We established and integrated that core data infrastructure that Alfredo showed. And then the next phase that could be done within the next year would be an advanced deployment, expanding to the entire US rather than just that northern Midwestern area. And then deploying an advanced integrated nested Laplace approximation model. This is an INLA model, and it has some benefits over MCMC. We were asked to do MCMC by our project sponsor, but it takes hours to run, whereas INLA would take minutes to run. It's deterministic, and it is used often with geospatial data. It's often used to fill in gaps in between weather stations for weather data. And so we think it would be a really good fit for basically filling in radon estimates in between the sensors. And then this would enable us to do real-time seismic risk modeling with this advanced analytical model. And the next step that would be needed, it would be conducting system-wide validation and robustness testing. It would have to kind of prove predictive capabilities and all of its capabilities to change the approach of the US government, which would be phase 3. After it's validated and tested its robustness, then the EPA, it would be very helpful if they could add radon sensors to increase coverage across the US between those sensors. Sometimes, especially in less populated areas, there's a really great distance in between those sensors. And so even with an advanced analytical model, the preciseness would not be quite there without some additional sensors. And then could move into this proactive state with earthquake prediction and preventative action here. And then hopefully this real-time interagency coordination across government agencies, including local, state, and federal government agencies. So thank you. That is everything for us.
Great, thank you very much. Questions? We actually have a number of our colleagues, Dr. Ruhi here, Dr. Filizadeh, they are from civil engineering, and also we have Chris here from Boolean Analytics. Do you have any questions from your perspective on this particular type of project?
So I have a quick question. So you mentioned that you've used MCMC to generate some earthquake scenarios and then to convert them or to translate them to the radiation, let's say. How did you do that? How did you map the earthquake scenarios to the radiation?
So I did a little bit of what can be done with MCMC regarding that. From my understanding is that you can actually predict the radon level out of the earthquake magnitude and the earthquake depth. I did not have previous knowledge of MCMC, but I knew that there is an equation. And that equation, as I mentioned, is based on the magnitude, and there is a factor of the magnitude, and those factors gets tuned somehow. For example, if you want to know the radon level for a specific magnitude and specific depth, out of historical data, you could know that and tune those. I can't remember the mathematical word for it, but those constants they get tuned so you could know the actual radon level based on the magnitude and the depth of the earthquake.
Okay, thank you.
Yeah.
Yes, please, Dr. Rui.
Yes, I say hi to everyone. Very exciting projects, and also thanks to Dr. Sabri for inviting us. I'm an earthquake engineer, so this was quite exciting for me. I was curious to learn more about how you connect to USGS, and did you have any challenges to access the data sets from USGS maps?
So USGS, we didn't for the data stream, we didn't actually connect it to the Exim Pro, which we used for data streaming. But actually, I did it before. I used the GeoJSON feeds. They are JSON feeds. You can use them in real time, keep them updating all the time, and get that data out of them. And there is the other API that talked about. It has a higher level of complexity. It provides you not only the earthquake depth or magnitude and location, it provides you even more detailed information about the waveforms of the earthquakes. And even I knew that you could know the station health itself about the earthquakes or each station. And you can query the other one. You can send queries specifically to what you need. But the other API that we used for our project, it provides us with not what we need. It only provides us with the magnitude, depth, and location, and that was enough for our pipeline. But yes, it is real time, and you can easily add it to any stream.
Great to know. Thanks for sharing that. I didn't know about this. This is great and relevant to our project. So maybe we can follow up later on if that's okay. Yeah, thanks.
Of course.
Any other questions? Okay. Amy, you mentioned that in-law is faster than MCMC. Have you tried in-law as well?
No, but I looked up how it works. It's deterministic, and it instead of creating all these samples that MCMC does, it really just finds an approximation, and its use cases are very similar to ours. And so while we didn't execute it in Python, it definitely seems like it would be the correct model, and it does run many times faster than MCMC.
Yeah. Of course, in-law is suggested as a uh, replacement for MCMC based on the mathematical analysis. What did you consider? What are potential challenges if in-law is implemented as compared with MCMC?
Yeah, so it doesn't capture the uncertainty quite as well as MCMC. So instead of doing all those samples, it finds an approximation, and so that would be a challenge compared to MCMC. But given that this is an emergency use case, we thought that speed would be more important in this case.
Yeah, thank you. Chris?
Yeah, hey, good afternoon. Yeah, really very interesting presentation. You may have mentioned it, and forgive me if I missed it. Did you guys run into Pager, Pager, by any chance?
No,
Yes,
I didn't run
we
across.
did, but I didn't mention it in the presentation.
You did? Okay.
Yes, I did. I had a look on it.
Okay, well, so I guess just for context, for the reason why I asked the question, and for the rest of the group, and thanks for, I'm glad that you ran into that. I mean, so Pager, there's a very similar path of what you guys are describing, where when an earthquake happens, it sends out a automated report, but that report means so much more, right? It sets thresholds for how first responders activate, and certainly there's entire protocols that if it hits a certain 5.5 with a certain depth, these essential elements of information are requested, and there's certain protocols that go out. And so I think that's very much what you guys were picking up on, of pushing it out through IPAWS. I'm glad that you're already thinking about that, but I think there's maybe a work that could be done of connecting this back with the Pager group. Pager also, as part of the Pager system, it cuts out a HAZUS ready file. So you can run HAZUS based on the Pager results. And so, I mean, the whole name of this entire system is just automation. So I was very impressed by what you guys were doing. So, please let me know if I can make any connections.
Thank you very much.
Thank you. That's great.
Appreciate that. I have another question, is about the PGM. Who knows what does PGM standing for? Probabilistic graphical model. Okay, so in PGM, you use some method for understanding what is the level of error. And if you remember, we actually talked about the PGM from the translating the physical system or physics-based model to the data-driven, or at least to running the digital twin for digital the physics-based models. So do you see any application of PGM in this case?
I mean, I believe that so in-law is a Bayesian analysis tool as well as MCMC, and I believe that Bayesian networks fall within the PGM analysis like umbrella. And so, yeah, I think for our future state, it would be important.
Yeah, thank you for that. Yeah, I was looking for this answer, and this is for everyone. Please go back and look at the PGM and Bayesian model, because I asked several times from everyone, how did you validate it? How did you bring the error propagated? You already have that in the content. So, and another limitation, because your case is data-driven digital twin, right? So, one of the challenges is insufficient abnormal condition, right? So, the earthquake impacting on the nuclear facilities, as Kosti earlier indicated, it doesn't impact the nuclear facilities because it immediately goes down. So you don't have abnormal condition to fit into your data-driven approach. So what would be the best way to kind of train your model and improve your model?
I think this is a tricky question somehow, because we need reality on both, on the earthquakes and the radon, if that's the goal. So maybe I'm thinking that if we really understood the historical data of the relationship between radon and earthquakes, let's say, and find a way, I don't know how, but maybe we can find a way to actually make a simulated data that makes sense. Like those high level of the data that we don't see every day, simulated, but in a way that's actually historical based, like based on maybe all historical rare events, I would say.
Yeah, I'm sure we could use some tools that will be able to train and score predictive models based on the historical rules. We could use, like you were saying, Kosti, synthetic data generation.
Mhm. I don't know the answer myself as well. So this is the limitation that we are dealing specifically for this case, and this limitation is applied to abnormal cases. I mean, insufficient abnormal information. Certainly, a very simple answer is synthetic data, more realistic. But what does that mean is really important, and is a matter of research for someone who wants to do a PhD on digital twin. Okay.
Yeah, one thing I said I think could help too is dedicated simulated evacuations and tabletop exercises, so that everyone's ready and can test certain parts of the twin before an emergency takes place.
Okay. Thank you, Ahmed.
No questions.
There you go.
Yeah.
Is this because you are sitting in the same lab with the team? You have to ask questions.
Okay. I'll ask one question.
Ask some questions.
Okay. Just a follow-up questions, like a question for what Dr. Sabri mentioned. Like you mentioned, you will use historical data for prediction. Like, do you think physics-informed machine learning or physics-informed approaches will be helpful in your case in terms of analytics and like even simulation?
I think so. I think the more data that we have, then we can make it, leverage whatever modeling that we can from a physical, to go along with our data driven model, make it more of a hybrid. I think that would be ideal.
Yeah, it's largely data driven, but I think in the future it could be hybrid as we integrate more of the like environmental data.
So what is the physics dimension?
Yeah, so there could be some like geospatial aspects to this, like in between the sensors, how radon is estimated in those gaps. And then I don't know, Alfredo or Kirsty, if you have additional.
I would say wind. I would say wind if you want to know the dispersion of the radon. If we have a physics model for the wind, to see maybe the worst cases where that radon would disperse or where would it go, I think that would be very helpful.
Ahmed, please ask one more question.
I don't have more questions.
All right, so this is this is not marathon, but at least half an hour presentation and question. Thank you.